curious, how many of you already work on inverse problems, something related to inverse problems? Let's see some hands. Yeah. Not so many. Actually, I didn't see some hands that I expected to see, but maybe you don't think tomography is an inverse problem, but it is. So who work on tomography, all right? Okay, so tomography, as you'll see, is an inverse problem as well. So anyway, maybe at least 1/3 of the audience is already familiar with what's an inverse problem, but the idea of this first lecture here is to set the stage for everyone, so hopefully you'll have an idea of what we mean by an inverse problem, and why we should be interested in solving inverse problems, and what are the challenges in doing so. Okay, so I have just 2 slides with the motivations. Here, the first one here, this is from a collaboration with some geophysicists in Naples. So Naples is a big city lying very close to an active volcano. So wouldn't it be nice to sort of monitor what's going on inside that volcano so you can run away if necessary, right? But you can't really dig into the volcano and take a look. So what you can do is you can do some measurements outside the volcano on the surface of the volcano. And from that you can maybe figure out what's going on in there. So what you do is that you run around here on the volcano. Actually, you fly on a helicopter around the volcano there, and you measure the magnetic field, right? And from those measurements on the outside of the volcano, you try to reconstruct what is the distribution of material, magnetic material, inside the volcano. And then you can see if something should be moving or bubbling a bit, and then it might be time to run away. So that's the inverse problem there. You can only do indirect measurements, right? You can't really measure the thing you want to know, but you can measure something like a derived quantity. So of course, if there's magnetic material in here, it generates a magnetic field that you can measure outside, and then you can set up a mathematical model, and from that mathematical model, you can figure out what gave rise to that magnetic field that you actually measure inside the volcano. So that's one inverse problem. Inverse problems also arise in image deep blurring. And here's one famous example where image deep blurring was necessary. The Hubble telescope, for the first couple of years, it actually produced pretty bad images that were blurred, and then they used a lot of the techniques like we'll be talking about here to actually deep blur those images to make them sharper. How can you do that if you have a blurred image? Well, basically, again, you set up a mathematical model of the relationship between the sharp image that you want and the blurred image. And then you use that mathematical model to try to reconstruct the sharp image. So again, the hidden information there is the unknown sharp image, and the data that you've got is the blurred image. Okay, so here's the setting for inverse problems. So as I said, it's always about somehow getting to know hidden information from exterior measurements. That's what we're doing here, right? And the situation is always that there's some kind of input that you generate, then that goes through a system, and you have a mathematical description of that system there, and then you measure an output from that system, right? And note that, so I say it's known, but the thing is that there are errors. These are measurements, right? And you can measure without errors, so there will be some errors in the data here. And then you want to know either the system or you want to know the input. So you have to know 2 of these quantities, and then you can find out the third one. This is always known. Sometimes you know this, and you want to know what was the input that gave the output. Sometimes you know the input and the output, and you want to know what was the system in there. So let me give 3 examples of that. All right, and now you can see there's a bit of kind of mathematical notation right there. I'm concerned with inverse problems in this part of the course that you can write in this form of an integral. Some kind of integration is involved here, an integration over a domain. Right, so image restoration is an example where you have this sharp scenery, but then you send the light through the lens, and then you record a blurred and noisy image. All right. So what you have there is, of course, you always have the data here, and in this example here, you know the system. Let me back up. Okay, so here's the system in the middle, and in connection with image restoration, you know the system because you can set up a mathematical model for the blurring that goes on in the lens, right? And so knowing those two, the lens and the image, you can compute the sharp image, the actual scenery. All right. Tomography is also an inverse problem, of course, but here the setting is a little bit different. Okay. So you start with an X-ray source. Okay. So you go down to your Radio Shack, you buy an X-ray source, and you send your X-rays through an object, and then you measure the damping coming out on the other side. On a digital kind of camera over there. See, what you want to know there is properties of the object. So this is an example where you know the input and you know the output. The input is the X-rays coming in. The output is the X-rays coming out and the corresponding damping. And what you want to know here is the kind of system that gave rise to that damping. So that's the object here. Seismology is another example of the latter. You have seismic waves going through some layers of the Earth. You measure the reflections of those waves, and from that you try to figure out where are these layers, and why do you want to know these layers? Maybe there's oil or gas or something interesting down there. Right. So the kind of inverse problems I'll be dealing with are of the form of first Fredholm integral equations of the first kind. So they look like this, right? And from the next lecture, we'll go into the numerical analysis part of the course. We will, of course, somehow turn this mathematical problem here into something that you can actually put on the computer, typically a linear system of equations, and then we'll talk from there, because once we have matrices and vectors, we can use MATLAB, we can do computations, we can get a lot of insight into the problem we are trying to solve. But I will spend actually the first lecture here on stuff related to the mathematical formulation, because that's what we do, and that's the name of the book. Or the subtitle of the book is Insight and Algorithms. So before you start computing, before you develop algorithms, before you solve your problem, you should know the properties of the problem you're solving. So first you should seek insight about what it is you're doing and what you want to do. So that's what we're doing in this first lecture here, right? So this is an integral equation. So it's kind of maybe the opposite of a differential equation. In an integral equation here, let me just see my next slide. Right? You have an unknown function. You have an unknown function f of t sitting there under the integration sign there. Then you have a right-hand side g, and you have another function of two variables, which is called the kernel, and it's sitting right there. So somehow a lot of these inverse problems that we'll see throughout this course can be formulated this way here. All right. Anyway, you see, looking a little ahead, we somehow discretize this problem, turn it into a linear system of equations. Let's say ax equals b, and boy, we know how to solve ax equals b, right? That's something we learn on the first semester, how to solve a linear system of equations. And in fact, it's very easy to do in MATLAB. You just write a backslash b, and that gives you the solution. So here I took a discretization of a particular test problem here, generated a 64 by 64 coefficient matrix A, and the corresponding right-hand side, and I solve that by means of backslash, and then I get the results shown on the left. And it looks interesting. And if you look a little closer, you'll see that the scale is actually 10 to the 16. So there's some humongous numbers in there. So maybe you didn't really quite expect that if you expected your solution to be around the order of 1, the magnitude, right? So actually on the right, I have shown two things. One is the exact solution to my problem. That's the dash dotted line that you can maybe see there. And then there is the solid line, which is a particular solution that I was able to compute by means of the techniques that we are going to discuss over the next weeks. So this is to motivate that maybe just naively solving AX equals B may not be such a good idea. Apparently there's something strange going on there. Maybe errors are magnified very, very much, so maybe we shouldn't do that. But why is that, and what should we do about it? So, yeah, so that's what this course is about. But it's not just about, giving you some algorithms. It's also understanding why we have these difficulties here. All right, so let me go through a tiny little problem here from chapter 1 that already illustrates some of the difficulties that we see when we're dealing with this kind of problem here. So I have here a least squares problem, a tiny least squares problem. The matrix is 3 by 2. It's, of course, artificially generated. It's a fairly ill-conditioned matrix. I defined it such that it is ill-conditioned. And then I have a noisy right-hand side, which I generated by multiplying the exact solution with A and then adding just a little bit of noise, a little bit of perturbation on that. So remember, the true solution is 1, 1. Okay? And you can see the perturbation I added is just very small numbers compared to the true right-hand side. So it's only a small perturbation, and we would think, it probably doesn't matter so much. Okay, so with this perturbation that I generated, there's no x such that the perturbed system is consistent, but I can compute a least squares solution, and so I can do that. And so there at the bottom, you see, sure enough, there's my least squares solution and the corresponding 2 norm of the residual. So the residual is pretty small. The residual is of the same size as my perturbations, right? So of the order 10 to the minus 2. Sure enough. So we might think it's a good solution, isn't it? We have a small residual. Well, if you look at the least squares solution there, you see the first component is 7, and the second component is around minus 8. And it's not remotely an approximation to the exact solution, which is 1, 1. So damn it, there's something rotten here, right, in the state of Denmark. So what is going on here? Why can't we even, for such a small system, compute a good approximation to our solution? And the reason is, of course, that this matrix is very ill-conditioned, right? Well, we could try something else. So just 2 wild guesses at other solutions. I don't remember how I came up with these guesses. But yeah, I wanted either one component or the other component to be 0, and then I computed the remaining non-zero component. And again, you see, for these 2 crazy guesses of solutions, I don't know if I should call them solutions. Again, we have small residuals, again, of kind of the same size as the perturbations that I added to B, but again, they really don't look very much like the exact solution 1, 1. Right, so already what we can learn from such a small experiment here is that small perturbations of the data of the right-hand side, they can actually lead to pretty large perturbations of the solution. And of course, the reason is that, as I mentioned, my matrix is ill-conditioned. Also, we can learn here that the fact that, if we have an x that gives rise to a small residual, a residual where the norm is small, that does not imply that this x is a good approximation to the true solution. So the size of the residual doesn't really tell us very much about the quality of x. So that's another very important lesson to learn here. So you have two options, right? Facing this problem here, you can say, it's too difficult, I can't solve it, right? I go home. I go home and I solve an easier problem. Or you can maybe try to do something about it. And if you're staying with me here for the rest of the course, this is what the course is about. What do? How can we somehow come up with techniques for computing reasonable approximate solutions to these kinds of systems here? So the key thing here to learn is that you somehow need to add more information about the solution you want. You have to give additional information in one way or the other. What kind of information you want to give depends on the particular problem you want to solve, on the physics or mechanics or whatever is behind the problem you're solving. So the mathematician can't a priori say you should do it this way. You should think about the physical problem you're solving and see from there, can I extract additional information that I can somehow put into my problem formulation. Right. In this case here, since it's just a small Mickey Mouse problem here, I assume that maybe I have a reasonable guess of an upper bound of the norm of the solution. So I know that the norm of my solution shouldn't be too big. It should maybe be of the order between 1 and 2. Maybe if the underlying physics told me that I can never have a reasonable x with a larger norm than delta. Right. So here, delta in this formulation here. So suddenly, when I add that information, I have a constrained least squares problem, right? So I want to find the x that minimizes the residual subject to this constraint that the norm of x cannot be larger than delta. And then I can, just to illustrate that this reformulation of the problem here can have a tremendous effect on the solution. Here are solutions computed with four different values of delta. If I say delta equal to 10, for example, so I allow the components of my x to be large, then I get a large solution there, and it's a bad solution, really. If I restrict the norm of my solution to be small, for example, 0.1, then of course I do get a solution with small elements in there. And again, it's not really a good approximation to the true solution 1, 1, right? But you can see if I choose delta of the order 1, I do get something that is closer to the exact solution. And actually, for delta equal to 1.385, I do get a fairly good approximation there, all right? But I can say this because I know what my true solution is. But what this illustrates, the purpose of this is to illustrate that you need additional information somehow. And you talk to the physicist or you talk to the guy in the laboratory or whatever, find some additional information on the problem you're solving, on the solution and so on, and then try to put that into the problem formulation. And what happened here is that instead of solving the unconstrained least squares problem, I changed it to a constrained least squares problem. And we're going to see that throughout, that instead of solving the original difficult problem, we turn it into another problem formulation that is less sensitive to errors. Okay. And then the course is about how do we do that, how do we implement it efficiently on a computer, and so on and so forth. Right. Right. Yeah, I guess that's what it says right there. Explain why we have ill-conditioned systems and why we always have ill-conditioned matrices when we solve these inverse problems. And look into these fundamental mechanisms. Use mathematics to say something about that. but also along the way see how we can modify the computational problem such that we compute a solution that's more stable, that's less sensitive to the perturbations, and in the end we want to do this efficiently on a computer, because in the real world we're not going to solve these 3x2 least squares problems. We're going to solve big linear systems of equations. So how are we going to do that? And what we'll get to very, very soon in these lectures here is like a catalog of regularization methods that you can use to do this. Right. I think, because this is now starting on chapter 2, so I think we'll just take a short break here for 5 or 10 minutes and then we'll continue.